Okay, in this video clip we're going to be talking about percentage yield, and by the end of this video you should be able to perform calculations to successfully calculate the percentage yield for instances where we've got an excess of reactants and indeed when we've got limiting reactants or rather limiting reagents also. Right, okay, so let's get cracking, shall we? What is percentage yield? Well, first of all, percentage yield is really just a measure of how successful a reaction has been. So let's say you were in a lab, you carried out an organic synthesis or a synthesis reaction, and you made a product. And all a percentage yield is really is a quantitative method of describing how well your lab practice was in addition to the actual reaction itself. Right, okay, so the way you calculate it is you have to use a simple calculation. You get the actual amount of the product divided by the theoretical amount of product and you multiply by 100. Now it's key to understand that these amounts, it's not okay to use masses, right? We need to use moles. So it's really important that we recognize that when we're calculating the percentage yield, we are indeed calculating the moles. And of course you just multiply this fraction by 100 to get a percentage. So let's get cracking. Let's start with an example with bromobutane and sodium hydroxide. You should recognize this as a substitution reaction because this bromine is being substituted by a OH, a hydroxide. And indeed it's nucleophilic because OH minus is the nucleophile. Hydroxide ions with a lone pair are, or rather is, the nucleophile in this situation. So we've been given in the question two masses. We've been given a mass of the actual bromobutane and we've also been given a mass for the alcohol. So what are we going to do? Let's work it out. Well, as I said, we never use masses. First step, work out the moles. So the moles of bromobutane, or rather 1 bromobutane, is 8.72 divided by the MR, which is 136.9. Stick into a calculator, which pops it out as 0.637 moles. So that is the moles of this reactants here. Let's have a look at the stoichiometry of the haloalkane or halogenoalkane to the alcohol. It's a 1-to-1 ratio. Therefore, the number of moles of the 1 bromobutane is going to equal the number of moles of butan 1-ol also. Therefore, the theoretical moles of product is going to equal 0.0637 also. So let's work out the actual number of moles acquired in this reaction. Well, we've been given the mass, 4.28. Again, let's use the formula moles is equal to mass over MR. 4.28 divided by the MR of butan 1-ol. The MR is 74. Let's work it out. Stick into so 4.28 divided by 74, and you should get 0.0578 mol. And this is the actual moles of product. Actual. So what's the last step? Well, we just stick it all into a calculator. Percentage yield, use the equation, of course, using the equation. Whoops, spelled yield wrong there. Oh god, that's annoying. Right, yield is equal to, remember the actual, which is 0.0578 divided by 0.0637 0.637 multiplied by 100, and you should end up with 90.7%. Now you might wonder, why have I left it at 90.7 rather than rounding up to 91? Well, we've been given the information in the question, the masses, as 3 SF. So I'd be remiss to not have the, or rather to give the percentage yield as 3 SF also. This is good practice. If the question doesn't state in an exam, use this policy. Whatever you're giving your information in, give your answer to that many significant figures. Okay, so that's the first one done, right? It's not difficult. Okay, so what I suggest you do is pause the video now, have a go at the question yourselves, unpause, and we'll go through it. Okay, so let's go through the question now. We've got the oxidation of ethanol to ethanoic acid. This is a reaction that you should already be familiar with. It's also a reaction. You may well be asked in an exam situation to write this, equation down. And indeed, you should be able to. You should be able to get the two oxidizing agents, the 2 moles of oxidizing agents and the 1 mole of water there. If you can't do that for OCR AS level chemistry in terms of F322, you need to go back and learn how to do that. Okay, and you'll of course recognize that the oxidizing agent in this case is, you should have guessed it, it's acidified potassium dichromate, right? Okay, so we're starting off with ethanol, and we've been given 2.8 grams of ethanol, and upon completion of the reaction we have formed 2.4 grams of ethanoic acid. So first step, yes, work out the moles. So ethanol, 2.3 grams divided by the MR is 46, and you should end up with the actual moles as being 0.05 mole, right? Let's have a look at the stoichiometry of ethanol to ethanoic acid. Yes, it's a 1-to-1 reaction. So the theoretical number of moles of product, which is the ethanoic acid in this case, is also 0.05. So let's work out what the actual moles of ethanoic acid is in this question here. Well, we're starting off with 2.4 grams. Let's divide it by the MR of ethanoic acid this time, not ethanol, ethanoic acid. The MR of ethanoic acid is 60. Let's stick into the calculator, work out what the moles are, and you should come up with 0.04 moles. So that is the actual number of moles of ethanoic acid, which is of course the product, and you should, as I said earlier, get 0.04 mole. So what are we going to do? Let's stick into the equation. Percentage yield is equal to the actual, which is 0.04, over the theoretical, 0.05, multiplied by 100, and you should get a nice figure of 80%. Again, just notice I've got the information in the question as 2SF. I've given the answer as 2SF also. Good exam practice to do so. Right. Okay, so again, that was pretty easy, right? It's not hard. So let's move on to a slightly more tricky example here. And this is where we've got a limiting reagents. So in other words, we've got a reaction, we've got 2 reactants, 2 reagents, and one of them we've got only a really small amount of. It's limiting, which means that it's going to limit the number of moles of the actual product formed. So let's have a look. We've been given this information here. We've been given 13.7, we've been given 10.9, we've been given 6.65. So we've got this reaction here, and we've got 1-chloropropane reacting with sodium cyanide to form butanonitrile. we're starting off with 13.7 grams of the haloalkane with 10.9 grams of sodium cyanide to form 6.65 grams of butanol nitrile. This is where students often make the mistake. The first step is identifying the limiting reagents, right? And a lot of you may think that, oh, you know what? 10.9 grams is lower than 13.7 grams, therefore sodium cyanide is the limiting reagent, right? You might think that is the limiting reagent. However, you'd be wrong if you thought of that. And again, it all comes down to moles. Remember, we're chemists, we work in moles, not masses, right? So we're talking about stoichiometry here. So we need to work out the moles to identify the limiting reagent. So it's one of these two, the haloalkane and sodium cyanide. It's not going to be the butanol because it's not a reagent, that's the product. So let's work out the moles of each one. Okay, so let's talk about the 1-chloropropane. We're starting off with 13.7 grams. The MR of 1-chloropropane is 78.5. Let's look at the moles. The moles, we should get 0.175. 0.175 mole. Let's do the same thing, but let's do it for sodium cyanide. Of course, it's not the limiting reagent, so let's just get that out of the way now. Let's divide it by the actual MR, which is 49. And you should get 0.222 mole. Okay, now clearly you should be able to see that 0.175 moles is lower than 0.222 moles. Therefore, the limiting reagent in this situation here is 1-chloropropane, not sodium cyanide. Okay, now that we've correctly identified the limiting reagents, let's work out the theoretical number of moles of butanol nitrile, which is just in this case the product. Butanol nitrile, yeah, good. And we should end up with, let's have a look at the stoichiometry between 1-chloropropane and butanol nitrile. It's 1:1. Whoops. It's 1:1. Therefore, we've got the same number of moles as the limiting reagent. Remember, the limiting reagent is limiting the number of moles of product we can actually form. That is the maximum moles of butanol nitrile we can make. So let's have a look at working out the actual number of moles. So the actual number of moles of the same thing should be, we've been given a mass 6.65 grams divided by the MR of this, which is 69, yeah, divided by, so let's get this stuck into a calculator, and you should get 0.09, whoops, 0.0964 mole. So now we've now got the actual number of moles, we've now got the theoretical number of moles. Let's work it out. Let's look at the percentage yield. Whoops. And of course, it's the same formula: actual divided by theoretical multiplied by 100. So actual in this case being 0.0964 divided by 0.175 multiplied by 100, and you should end up with 55.1% as a percentage yield. That's all there is to it, folks. That's all there is to it. We've covered percentage yield in terms of excess. We've covered percentage yield in terms of limiting. You might wonder, why is it that we're getting less than 100% really? Number of factors. A, reactions don't always go to completion. They may have, the reaction may be in equilibrium, right? There may be other side reactions going on. We may form byproducts. The reactants we've started off with, the reagents we've started off with may well be impure, leading to decreasing the percentage yield. It may well be that in a normal synthesis reaction in the lab, we're transferring the reaction mixture between different flasks. So of course, at some point, or if we're going to remove the solvent and all these fun stuff using a rotary evaporator, we're going to lose some sort of product, whether in the recrystallization or in any other format. We will lose some product in the reaction vessel. Therefore, we're always going to get something less than 100%. Okay, that's all there is from me in this clip. I hope it helped. If it has helped, if it hasn't, let me know on any suggestions. What would you like to see in the videos following, and so on and so forth. Until next time, bye.